Welcome everyone, including our people online. My name's Andrew Woods and I'm manager of the HIVE, welcome to the HIVE. Our presenter today will be Daniel Adams, who is giving our third presentation in our new Photogrammetry network series of presentations, all using photogrammetry in one way or another. So the talk today is a little bit different from last week. It'll be shipwreck related, focused on the Santo Antonio de Tanna shipwreck. And Daniel is a graduate from the computer science degree here at Curtin University and has been working with the HIVE for maybe the past 4 years? Even when you were finishing your degree, you did a project here and that sort of led one thing to another. So without too much more ado, I think I'll pass over to Daniel and let him talk about the Santo Antonio de Tanna.
Thank you. So hello to everyone who can make it here in the HIVE today, and to those who are currently watching this session on YouTube. So what I'd like to do today is to take you through some of the techniques and workflows used to generate a complete 3D reconstruction of the hull of the Santo Antonio de Tanna as it was excavated and surveyed between 1977 and 1980. So this work is the continuation of a project undertaken by a Curtin HIVE intern, Lachlan Shaw, in 2018, who focused his efforts on the bow section of the wreck site. So previous attempts to reconstruct the stern section at the time had unfortunately been unsuccessful, and so I was contracted by Jeremy Green to first revisit and reprocess the bow section of Santo Antonio de Tanna, and then to try and reconstruct the stern section, and then finally align and merge those two sections of the hull together to form a complete 3D model of the entire wreck. So in this presentation, I'll use the term legacy datasets to refer to photographic datasets that were collected in a previous generation of underwater survey, and more specifically before photogrammetric 3D reconstruction processing, or as I'll refer to, P3DR processing for short, was commonly available. So the application of P3DR processing on legacy datasets can provide a much richer cognitive understanding of underwater sites as compared to hand-drawn site diagrams. They can be a source of new information. They can allow archaeologists and the broader public revisit and explore underwater heritage locations that are essentially frozen in a time capsule from 50 years ago. So in the case of Santo Antonio de Tanna, where the underwater survey and excavation work occurred over multiple seasons, visualizing the wreck site completely uncovered and whole as it rested on the seafloor was not even a possibility. So this inability to visualize the wreck site would also be exacerbated by poor visibility underwater. So just a way of a background here, Santo Antonio de Tanna was a Portuguese frigate built in 1680. It had sunk in 1697 and was discovered in the early 1960s, just there on the bank of Fort Jesus in Mombasa, which is located on the Swahili coast of Kenya. So Santo Antonio de Tanna was originally sent to Fort Jesus in 1967 to relieve the fort, which was under siege by the Omani Arabs. When it arrived at the fort, they discovered that all the Portuguese had been killed and at the fort, and the fort was being left defended by 25 Swahili men and 60 Swahili women. So after unloading their supplies, the Santo Antonio de Tanna came under fire from the Omanis, and during the battle became lodged on a nearby reef, which is just where that arrow is pointing. So once the tide fell, the ship capsized and sank on the bank of the river. So prior to the introduction of digital cameras, where thousands of images could be stored on an SD card, the process of using cameras underwater was rather finicky, to say the least. It's also quite time consuming. So film cameras were usually limited to to a maximum of 36 shots per roll before someone had to swim back up to the surface, take the camera out of the waterproof housing, take the film out and reload the camera before putting it back into the housing and swimming back down to the wreck to continue the survey. So even so much as a grain of sand on an O-ring seal could be enough to result in water leakage in the housing and could damage the camera. So during the survey of the Santo Antonio de Tanna, 2 Nikonos 15mm lens cameras were used to capture stereoscopic image pairs. Both cameras were set up on a stereo bar with 1/2 meter separation and then calibrated underwater. So the stereo bar was then attached to a photo tower, which you can see there on the left. So whether a particular data set is suitable for reliable P3DR processing will depend on a variety of factors, some of which can negatively impact the quality of the reconstruction and others completely reduce your coverage of the model. So some factors would include the amount of turbidity in the water, the quality of the lighting, the amount of backscatter in the images, the amount of sand that might be floating around in the water, sharpness of the photography, the amount of motion blur, the amount of film grain or sensor noise in the images, but most importantly, how much the environment changes from image to image. So the key requirement of photogrammetry is that the object or environment being reconstructed needs to remain static during image capture. And so at this point, I'll remind you that the bow and the stern sections were only uncovered during the season that they were excavated and photographed, meaning the amount of digital content that can be used to actually align the two halves of the ship together is fairly limited. So fortunately, in the case of the Santo Antonio de Tanna, image overlap is fairly good with usually minimal blur and generally good film exposure levels. So we were also very lucky that there was sufficient 3D model coverage on the keelson, the mast step, and the planks that I'll show you later are known as the thick stuff to join the two sections together. So the conventional photogrammetric 3D reconstruction workflow consists of several steps that you'll probably be familiar with. Feature extraction, feature matching, bundle adjustment, sparse reconstruction, depth map generation, dense reconstruction, mesh generation, texturing the mesh, and then generating an orthomosaic. So this particular data set presented a number of challenges that would otherwise prevent turnkey 3D reconstruction packages such as Metashape from being able to generate a full 3D model from the entire data set in one go. You know, we wish it was that easy, but as some of you will know, it's not that simple. They can be pretty temperamental, these packages. So for this reason, a number of additional distinct processing steps and a modification to the workflow was necessary. So these additional steps consist of a data pre-processing, reconstruction of the bow and stern sections separately, and this would involve a full mesh reconstruction and texturing from the depth maps, meshing from the depth maps rather than a noisy dense point cloud. And then model assembly, which is sort of using manual markers to piece together all the chunks of the reconstruction like pieces of a jigsaw puzzle, including the two halves of the shipwreck. And then complete reconstruction, which is just continuing on the standard workflow. And then finally, the orthomosaic generation. So as a first step, each image underwent a contrast-limited adaptive histogram equalization prior to the feature extraction step to better define the edges of the objects. So while normal histogram equalization can be used as an effective tool to stretch out the intensity range of an image by transforming each pixel, it has the tendency to over-amplify noise and can create large, ugly changes to the global contrast if the image contains clusters of extreme bright or dark spots. So an original scanned image is shown on the left, and the enhanced version you can see there on the right. The application of CLAHE for short. It can also translate to a night and day improvement on the final 3D model textures. So areas in the photography that were required to be digitally masked out prior to processing, such as divers and excavation tools, rubble and debris. This is stuff that would normally move around the site. You don't want to try and align those features. So also, when you scan physical film negatives, the edges of the film reel will often be included in the scan, and we don't want those borders to be imprinted on the final texture, so it's better to mask those sections out. Another thing is the visible photo tower. They can also be a hindrance to P3DR processing because the photo tower moves with the camera and it's always present, and it can create sort of strong persistent features in the data set that can sort of lead to incorrect alignment, and that will just break the reconstruction. So as a proof of concept, the previous work by Lachlan Shaw involved taking 570 images of the shipwreck, 276 images captured in 1980, and then 294 images captured in 1979, then processing it with Photoscan, now known as Metashape, to create a 3D reconstruction of the bow section. So while the reconstruction of the bow section was more successful, with the exception of the obvious errors seen in the DM on the right, all attempts to reconstruct the stern had failed using the traditional workflow. And you can see that sort of flat spot is an alignment error. I think usually if two images are too close together, they'll sort of treat all the features that are detected in those two images as like a really strong match, and then they'll just say that's where those images are, and that you won't get any depth from that section. So now, the reason it failed was due to a number of reasons, including lower quality scans, lower contrast without using CLAHE, but maybe not so rigorous marker placement, but also not being able to take advantage of the new image alignment strategies that the HIVE team have developed over the last year. So this work was published as a report. You can see there. I can send you all a link if you like, on the WA Museum website if you're interested in reading about Lachlan's project. So around 80 control points, also known as markers in Metashape, were used in most of the 603 images that I had access to act as a guide for the bundle adjustment algorithm. So these markers were primarily placed on the corners of ship's planks, patterns and cracks in the wood, and even seashells. Markers proved absolutely necessary to include photography which otherwise could not be aligned to the central reconstruction for unknown reasons. We found that often troublesome images would still easily be used to generate smaller isolated models, which we could then align and then merge back into the primary reconstruction with markers. So this method was invaluable to filling all the gaps in the primary reconstruction. So now I'd like to take you on a short virtual tour of our 3D model of the wreck site, starting from the bow and moving to the stern. Firstly, pointing out that this section of the keelson, that's a little blurry. This is an example of where a separate high-altitude image set was used to generate an isolated 3D model and then merge back into the primary reconstruction with markers to fill in the gaps where processing had otherwise failed. So now we're approaching the center of the wreck, and most notably the mast step. Well, I'll mention at this stage, this is the edge of the 1979 survey. You can still see a little bit of the rubble where the data set ends and the 1977-78 survey of the stern begins. So these are three extremely long planks that I previously referred to as the thick stuff, run almost the whole way down the ship's length, which is approximately 38 meters. So as we spin around the model, it should start to make a little sense, or a little more sense, what the ship might have looked like if it were whole. So the straight keelson running down the center of the ship with the mast step logically placed in the middle. The remaining timbers on the port side of the hull actually resembling the curvature of a boat. Now this is the view from the other angle, shows the port side of the Santo Antonio de Tanna that ended up resting a little flatter on the reef. The reason there are more timbers preserved compared to the starboard side is because over 280 something years, those timbers would have collapsed under their own weight, and the whole as the whole ship rested only on one side of a rather steep riverbank. So I think it's just incredible the high level of detail this model shows. Being able to visualize this site in great detail also is a testament to the high quality of the photography. Finally, I'll add that these 3D models are not limited to viewing on a flat screen. They can easily be loaded into a VR headset, allowing you to travel in time to the 1970s and walk on a virtual deck and explore the site as an immersive experience. So I will give you a chance to sort of put on 3D glasses in a bit, and we can have that sort of wander around the wreck site. So in the 1970s, the process of constructing a 2D photomosaic involved printing the images at a consistent scale and then cutting and gluing the images together. So a 2D photomosaic produces a flat image of a three-dimensional object, which is essentially a distortion of the original scene. So this is most evident in the shape of the keelson, which archaeologists understand to have been straight, but note you can sort of observe a noticeable downward bend in the initial orthomosaic. Generating an orthomosaic from the 3D reconstruction has the advantage of being relatively free of this kind of distortion. So as you can see, it's sort of bent down here, and that's a little bit more straight. And see, these thick stuff is also slightly differently shaped. This is the Lauchlan's original. So what I'd like to do is conclude with the image of our full orthomosaic, and by reiterating that this presentation has discussed a modification to the traditional P3DR workflow used to reconstruct and merge the full hull of the Santo Antonio de Tanna from the photographic surveys conducted between 1977 and 1980. As many of us are familiar by now, it's often the case that simply trying to process a full data set in one go will fail and result in an incomplete model. So in this case, the 3D reconstruction of the Santo Antonio de Tanna using Agisoft Metashape, alongside the non-traditional techniques we have outlined, provides the most comprehensive understanding of the shipwreck site to date. So thank you for listening. Just jump to the 3D viewer and hand out some 3D glasses.
Do you want to show the Metashape
Oh, yeah, sure.
first?
So this is the Metashape reconstruction. Like my mouse. Yep.
So Daniel, you talked about putting in the markers. So those were manually, you put those, you were able to manually put those
Yes.
in Mesh? Because normally it kind of is behind the scenes deciding that.
So the way you can, there's two ways you can place markers. This is also the second part of this project that Jeremy's been working on. But there's two ways you can place markers. You can place it on the 3D model, and they get reprojected back onto the images, where you can refine their position on the images. Actually, there's three ways. That's one way. The second way is you've got an alignment. You place a marker on the image, and then it gets projected into 3D space, and they appear on the model. And then the third way is before any alignment, you're placing a marker on an image, and then you're placing that same marker on a different image and saying these two are linked via this marker, and that can help in the image alignment.
What do you do for this one?
All three. Yeah.
Are they pseudo ground control points then?
Yes. Yeah, they're in their own local coordinate system. Yeah. Sorry?
Show the camera.
Oh, yeah.
So turn off these markers.
So this is the images that were used. I think this one, 568 cameras, 405 aligned. It's fairly good. Now, I don't have it in this project because it's a bit hard to navigate, but usually with Metashape, you end up having so many different chunks that are, you're experimenting with image sets, you try and build a reconstruction, based on the amount of coverage that you have in that reconstruction, you place models that might align with another reconstruction, then you sort of align those chunks and then merge those chunks, then continue until you progressively build a shipwreck. Sometimes the exposure in the images are different, and so that can stop it from aligning. Sometimes they're too far apart, but I found that sort of method of generating little jigsaw pieces to fit it all together, it's quite useful. And so I'll turn this off for a second, and you'll actually see, mentioned in the video, you can just sort of see the curvature of a boat. That's the mast step that would run straight down the center, and then that's the curvature going upwards. And then these are the thick stuff.
How long is it?
38 meters. And
So what is scale?
pardon?
So what is scale?
No. No. But if I jump to the 3D viewer, and I can hand out some glasses for you. Oh, thank you. Is this one on? So this is 11 meters wide, by the way, the beam. Yep, you can see the 22.
I wonder if he's trying to mix it up.
Online will not see the 22. You can put 3D glasses on, but it won't.
Just gotta turn this way.
What's worth pointing first?
Yes.
I'm sure you make lots of news now for those who
So get ready, because you're about to time travel. This is the closest thing I think we'll have to real time travel to the 1970s.
Very impressive. You should be very pleased. Yeah.
So this is how, it's not exactly how it was lodged on the reef, but because I don't think it's in its sort of local coordinate system. It hasn't been like georeferenced or anything, but it's sort of an indication of how it was sort of like perched up on the riverbank. That in the thumbnail of the Eventbrite, you saw sort of an image of a diver. I think it's actually in the first. In this the background here, you can see how sort of extreme the angle was, or that they were dealing with. Here, and yeah, it's sort of it's pretty fascinating how much detail you can get from all these black and white images. They're all captured pretty high quality for the purposes of creating an orthomosaic by printing out the photos and sticky taping together and then rescanning them. But the technology has come a long way.
Pretty cool, and some of them you can see some of them, particularly that you get some of that wood texture, which is pretty cool.
Yeah, I think these are calcified nails. All these white dots.
Yeah, either side of them.
Yeah, you can see even some rubble.
You tempted to try and colorise it?
What colour?
You've been busy enough with this, but yeah, that'd be a fun exercise.
Yeah.
And how does the model sort of fall away as you go into those occluded sections, where you can see underneath some of the beams?
So you can see this rubble here.
Yeah.
That would be the separation point between, sorry, up, so you can see this whole thing. That would be the separation point between the two seasons.
Yeah.
And so when this part of the wreck was imaged, all of this was covered in rubble and sand. And then they also, part of the process of excavating, when they come back the next season, usually they do all their survey work and then they rebury it just to protect it from the underwater sort of elements. And so, yeah, that section was covered when this section was surveyed and excavated, and then vice versa. And so, yeah, you sort of have to be very careful about where you want to align and merge the two chunks together, because then obviously artifacts that will show up from, this section of the model that it's obviously not a flat surface. It sort of looks a bit strange. And there's also some areas in the reconstruction that sort of were due to poor overlap and some poor image quality. But you can sort of see how the algorithms sort of try to guess where this part of the keelson is supposed to be, but has obviously sort of failed in this section here. But I think it's done a relatively good job. I've started using the depth maps as a way of meshing the model and using extrapolating from the depth maps rather than interpolating from a dense point cloud. And that's because the dense point cloud is often still quite sparse in a way, and when I sort of compare both methods, the reconstructions is just full of gaps. It's full of holes, and even if you use extrapolated settings in Metashape on the dense reconstruction, it sort of looks a lot weirder and doesn't look smooth at all. And so I thought this is a much better way to sort of do that process. And now I just do that for all of my reconstructions. And it's also a lot faster as well.
You might have done the texture off, do you think?
Sure. I have to do that in Metashape. So this is Petra asked, can you turn the texture off? So,
She wants to see the 3D model.
yes.
I can see.
I'm waiting for Petra to say how.
Here we go. So this won't be in stereo. Actually, it might be in stereo because, yeah, there we go. But it's just not geometrically correct because of the, yeah. I might turn that off, that looks strange. Yeah. Yeah, so you can sort of see the, is there any point that you're sort of wanting to focus on?
No, I thought that was what Peter was reading always sometimes at the lines.
Yeah,
So
yeah.
I
So
asked to turn the texture off because you can see it better.
Ah, okay.
I think what's
Yes.
clear is the improvement from the initial efforts,
Yeah.
and it shows to me that when you have a complex data set that you can't get away with just accepting the default. You have to dig deeper
Yeah.
at different steps, and you've done very well at doing that.
Yeah, the way I see it, oh sorry.
Many areas of the mesh underneath is considering the quality of the images, because Lachlan took him 3 months to get something out of it. It's a pretty good reconstruction.
Well, I think the way I see it is I max out the key points when I do the feature extraction. So usually I use 5 million key points and then take the tie point limit off and just set it to 0. And even if there's noise in the sparse reconstruction, you can manually edit that out. And I sort of see it like if the depth maps are going to be generated from the sparse reconstruction and the model is going to be generated from the depth maps, you might as well have as much data as you can to start with, and then you just sort of chisel away like a piece of marble. You can remove noise later. You can't add more detail later. So I think that maximum quality to start is sort of has like a trickle down sort of effect towards the end. Yeah, so you get lots of detail. You get geometry in the calcified nails, to be honest.
You mentioned the various
Well, it looks pretty cool. Sorry, Ian, but you can see the names. So it's
Yeah.
not on the texture, not just on the texture, it's actually on the model. So
Yeah.
sorry.
I'm all for admiring. It is a very impressive model. Now, I was curious, you mentioned the numerous challenges with different, when images aren't, you see a lot of models taken in crystal clear waters and things, and this is a real challenging data. I mean, I was interested in that. Some of the kind of, like the visibility, the backscattering you get in the water, that's effectively masking what you're trying to photograph. Do you just mask those? How are you dealing with like the scatter in the water column? Did you have any tactic to do with it? You just
No, if it's in front of the stuff that you want to reconstruct, you sort of have to keep it there.
do you keep? Oh, is there an option? Did you play around with maybe masking it so Metashape didn't mistake that for your target?
No, it's too much. It's too much. If it's tiny speck, it's so much masking.
That's
I think.
what I was wondering.
Yeah.
Is, I've seen some data sets where it's pretty full on. I'm wondering if there is any strategies. I mean, the old image fine, but when it's, I imagine it.
I think I might have actually put that in a different project. It's not accessible on this machine. Actually, this might see how. Oh, what? No, that's not the one. I'll just bring up the actual metashape. Oops. Yeah, okay. Yeah, I can show you later. That's the getting a bit sidetracked.
And again, what's interesting towards there's numerous iterations.
Yeah.
Yeah, and you're able to kind of quantify, you know, the kind of number of iterations that you had to get to this kind of level at the different steps. How many iterations?
Gosh.
So tens or hundreds?
It's really, I mean, with the way I mark iterations is this sort of panel here. If there are too many chunks that I have to scroll too far, I create a new version because, yeah, it just gets...
That depends upon us getting a bigger screen.
Yeah.
I think we're going to need a bigger screen.
Yeah.
Who would have thought you could say that about the Hive?
Yeah. Yeah,
I think that's answered the...
Yeah, there's definitely been some projects which just keep stacking all these chunks that you experiment one way, experiment the other way, and then you have to compare the two, and then aligning the chunks, because there can be, I think one other project was another shipwreck called the James Matthews, and I think there was something like 23 photographic survey runs across the ship's hull, and the camera had to be leapfrogged. Oh, sorry, there was two railings that went across the hull, and the photo tower sat on the railings, and then the camera was slid across the railings, imaging sort of a run of the ship, and then the photo tower had to be leapfrogged across the entire shipwreck. And so every one of those sort of runs were their own separate reconstruction that I would have to align with markers sort of together. And so you're not aligning and merging them all together at once. You're sort of aligning two chunks together, generating a full 3D model. And so you can say like chunk 1 and chunk 2 get merged into sort of like chunk 3, and then that has to be aligned with all the other chunks, and then everything blows out kind of thing. Yeah, so you sort of have to mark versions with just a fresh project. And it's also, I think this project could have been like 50 gigs just for each one of these project files, because there's so many 3D models and so many points that you're sort of duplicating, and yeah.
We might wrap up the formal part of this now, and people are welcome to hang around afterwards. Please join me in thanking Daniel for this presentation. Grab the microphone from me so people can hear me. We are doing lots of work on different shipwrecks, and each project requires just slightly different technique in each case, and so it's nice to be building up a sort of a body of work which also builds up new techniques and capabilities. Our next presentation in this series of talks will be on the 30th of June, be presented by Morgan Titmus and Gary Whitaker from the Curtin Medical School, and they'll be presenting on roughly the topic of creating 3D models of anatomy samples using photogrammetry, and they've been getting some really good results. This will be an in-person session only due to the requirements of the WA Anatomy Act. We cannot put that content online. So make sure you come into the Hive that day, and we'll be circulating information about that particular session shortly. But otherwise, thank you, Daniel, and thanks for joining us, and thanks for joining us online.